So we're back, Chemistry 3053. Last class period, we talked about enthalpy and entropy and some of the concepts that have to do with reactions, which we're now going to look at, types of reactions. We're going to look at equilibria and kinetically controlled reactions. So what you're going to see is that equilibria are thermodynamically controlled reactions, and just the normal reactions, the vast majority of reactions that you'll deal with in this course are kinetically controlled reactions. And so we're going to start looking at the differences in those and look at some of the reaction diagrams, some of the potential energy diagrams, to analyze those and see how they pertain to these two types of reactions and see how they are different. So to start out with, here is an equilibrium, an exergonic process. Now remember that is analogous to exothermic, except now we're talking about gives free energy, and it simply means that the products are lower in energy than the reactants. So this is a typical reaction coordinate diagram. And so the products are favored to form spontaneously. When you first mix A and B, you don't know how long it will take to reach the equilibrium. Here is the equilibrium, A and B go to C and D. Eventually they'll reach equilibrium. There will be a certain amount of A and B and a certain amount of C and D in existence when equilibrium is attained, and you don't know what that is, but you can calculate it if you have the equilibrium constant. And we're going to look at that just a little bit. The greater the magnitude, the larger the number of this delta G that gives free energy difference, the greater the products will be represented. So, why does a process like this, which is an equilibrium process, why does it not react to give only C and D the way that the kinetically controlled processes do? And you can draw this energy diagram to see what is happening so that it'll help you understand it. When you first start out, you have only A and B when you first mix these two. And over here at the other end, this is what it would look like if you had only C and D. This is the amount of energy in the system. Over here, this is the amount of energy in the system when you start out. But remember, nature works towards lowest energy, and so the process, A and B, could be converted to C and D, and then C and D will be converted back to A and B. And that will continue to happen until an equilibrium is reached, and that equilibrium will be reached at the lowest energy, when the lowest energy is attained. And so this is the minimum value. This is a minimum on the plot, and this has the lowest energy. The equilibrium constant, which you've calculated before in general chemistry, I'm sure it's used to show the degree to which a reaction is the products are favored or the reactants are favored. And here, this is just simply the way that the Gibbs free energy is calculated if you know the equilibrium constant. So these are the thermodynamic terms. These are used to describe relative stabilities of the products and reactants, but you don't know anything about the rate so far. Okay, so notice that increasing or decreasing the value of delta G by about 6 kilojoules per mole corresponds to a 10 times change in the equilibrium constant. So if the equilibrium constant is 1, think about that, what that means. If the equilibrium constant is 1, that means that the concentrations of reactants exactly equals the concentrations of products. And so, of course, that tells you if they are exactly in equilibrium, if they equal each other exactly, that means that they have the same energy. And that's what this tells you. So the percent of products will be 50% because the percentage of reactants would be 50%. So if they are exactly equal, the equilibrium constant is going to be 1, and the delta G will be 0. So what this is telling you is that this over this exactly equals 1. That means that this product is exactly equal to that product. Okay, that's what was being discussed over here. So if you change this by about 6, it converts this by about a factor of 10, the equilibrium by a factor of 10. Okay, and so that is telling you that the percentage of products will be either 90% or 10%, depending on whether they're favored or disfavored energetically. And so that's a large influence. A factor of 10 in the equilibrium constant is a large influence in the percentage of products. A reaction, just so that you'll know, a reaction that's giving a 90%, say, yield is considered a pretty good yield. So a negative sign for delta G tells you that the product is favored, but it doesn't tell you anything about the rate or the kinetics for the process. Delta G says nothing about how fast a reaction will occur. And that's because it pertains to equilibria. Some spontaneous processes are fast, such as explosions, but some of them are really slow. In the example that is given is the conversion of carbon in diamond form to carbon in graphite form. Okay, even though it's spontaneous, it takes a long, long time. The reaction, now, we have just switched, notice, we have switched from equilibria to kinetics. And so in a moment, we're going to have a diagram, and I'm going to stop at that time and show you on the diagram a very easy way to understand the difference between a kinetically controlled reaction and a thermodynamically controlled reaction. A reaction that is governed by kinetics and an equilibrium. They are two entirely different processes, and it's very easy to tell the difference, and I'll show you in just a moment. But the reaction rate is a function of, it can be influenced by a number of things, and here are some: the concentrations of the reactants or products, the activation energy, which we're going to see in a minute, so you'll have to be just a little bit patient, the temperature of the reaction, the geometry and sterics, and that's going to be related to the activation energy. The geometry and sterics, how easy it is for the molecules to come together and react, will influence the activation energy. These two, number 2 and number 4, are somewhat related. And then the presence of a catalyst. A catalyst can, as you know, can influence the pathway of the reaction. It gives it a new pathway that is lower in energy. And if it's ever not lower in energy, then the reaction will simply go back to the previous pathway and bypass the catalyst. The catalyst will just sit there as a spectator molecule. So rate equations. Now we're coming to the rate constant. The rate is determined using a rate law. The rate of the reaction is described by a rate constant times the concentration of the starting materials. Okay, and so the rate depends on a rate constant and the concentration here. And we're going to look a little bit more at these, the order of a reaction is represented by X and Y as follows. So the order of the reaction is, here we have, let me back up. The rate of the reaction is equal to the rate constant times the concentration of A and the concentration times the concentration of B. Now, A is taken to the X power, and X is the number of molecules of A that are involved in the rate determining transition state, and we haven't gotten there to that yet, but just keep that in the back of your mind. The A is one of the reactants, and X tells you how many molecules of A are involved in the reaction. So if 2 molecules of A are involved, then this will be A to the second. If 1 molecule of A is involved, it will be A to the first. If if 2 molecules of B are involved, it will be B to the second. If 1 molecule of B is involved, it will be B to the first. And so the order of a reaction is represented by X and Y, and you simply add X and Y. So if this is A to the second power, B to the third power, the order of the reaction will be 5. Okay, so this is a first order reaction when you have, say, for example, 1 molecule just falling apart or decomposing. And so the rate will be influenced only by that 1 molecule, the reactant that is falling apart or decomposing. If you have 2 molecules coming together in the rate determining transition state, the rate will be the rate constant times the concentration of A times the concentration of B. And this will be second order because it's A to the first power, B to the first power. 1 plus 1 is 2. And so here, this will be second order. Here, most of the reactions that you're going to see are going to be first order or second order. It's very difficult to get beyond second order. There are some, I don't know that we're going to cover any, but there are definitely some where the rate of the reaction is equal to the rate constant times A squared, the concentration of A squared times the concentration of B. This is third order, 2 plus 1. As you go up in numbers, it becomes less frequently observed, okay? But simply because it's difficult to have a large number of molecules all come together at once and react simultaneously as one group, okay? So usually things occur more stepwise. So it will be 1 molecule falling apart or 2 molecules coming together. Occasionally, 3 molecules coming together, and beyond that, it's very rare. Here, if you double the concentration of A, the rate is doubled, obviously. Here, if you double the concentration of A, the rate is doubled. Okay? Here, if you double the concentration of A, since A is taken to the second power, the rate is quadrupled. Okay? So that's just a demonstration of the way that the concentrations impact the order of the reaction. Factors affecting the rate constant continued. The activation energy, remember this is one of the things that was on that list. You can go back and look at that list. E sub A is the activation energy. Energy of activation, okay? And what it is it's the difference in energy between the reactants and the top of this energy hill. This is a plot that gives you information on the energies of the reactants and the energies of the products, and it also shows the energy of the rate determining transition state. This is an energy maximum, okay? And this is going, so you're starting out with the reactants, you're going over this energy hill and then down to the products. And since we're talking about energy of activation, this is going to be a kinetically controlled reaction. Typically, when you're talking about equilibrium, you're not talking about this distance. So you're talking about the distance between reactants and products energetically. So this, when you're talking about E sub A, you're talking about a kinetically controlled reaction. When you're talking about rate constants. Now, the reason that this is going to be a kinetically controlled reaction is because the reactants have enough energy to get over this barrier. But once you go downhill like this, the products don't have enough energy to get back over the barrier. They get trapped on this side of the energy barrier. And so they can't get back. And that means that you don't have an equilibrium because the energy hill is too high. It can be attained going forward, but it cannot be attained going back. So your reaction is just in one direction. So this is the lowest energy pathway, okay, connecting reactants and products. And so you might go over some other pathways, that are going over higher energy hills, but nature always seeks lowest energy. And so nature is going to take the lowest energy pathway. So that's the pathway that's shown by that red line. As the energy of activation increases, the number of molecules possessing enough energy to react decreases. Now let me go back. What we're talking about, remember, is the barrier here, the height of this energy hill. This is E sub A. Now on the next one, let me point out one more thing. Here, energy is on the vertical axis. It's on the y-axis. Now let's go forward. This is going to seem confusing possibly because now energy is on the horizontal axis. So we're talking about something totally different. Now we're talking about the number of molecules in the system, in a typical system, that has that enough energy to get over that barrier. And so initially, not all molecules will have enough energy to get over that barrier. So only some will have enough energy to get over that barrier. And if you increase this energy, you're going to have fewer molecules. If you decrease the energy, you're going to have more molecules. So this shows, just the sort of the common sense that tells you that as you increase the amount of energy necessary for the reaction to occur, it's going to be harder for the molecules to get over that border. So that's what this diagram is telling you. The lower the activation energy, the faster the rate, because it will be easier for the molecules to get over the barrier. Here they're going over a lower barrier, now they're having to go over a higher barrier. And so this reaction is going to take place faster. This will take place slower. Okay, so the energy of activation influences the rate of the reaction, which is the point, which is what we just said. The temperature, raising the temperature will result in a faster reaction because as you raise the temperature, more molecules will have that energy that they need to get over the barrier. So it will help the molecules possess enough energy to get over the energy barrier. A lot of this just is sort of common sense. Steric considerations. The steric hindrance and the geometry of a compound affect the rate of the reaction. When the molecules collide, they have to have the correct orientation. You're going to see a lot of that before. So in the next few chapters. So for example, if the molecules need to come together like this in order to react, and they come together like this and bump and collide, and then they bump and collide, they bump and move away, and then finally they'll bump and come together in the direction exactly the way that they need to react. Remember, I talked earlier about the populating the antibonding orbital. And so if the molecules are coming together so that that anti-bonding orbital is not occupied, if the molecule is donating the electrons, is coming forward in a way such that that lone pair does not occupy the anti-bonding orbital, you're not going to have a reaction. And so this is important. Also, if there are large groups on one of the molecules, it can make it harder for them to come together in a way such that they can react. Conformations can be important also. The molecule may need to change its conformation. Remember, we talked about the different conformations of the molecule, and ring flips and anti and gauche sin. Some conformations of some molecules can be very important for the reaction to occur. You will see that in some cases also. Now, catalysts and enzymes. A catalyst speeds up the rate of reaction without being consumed. Enzymes are catalysts. A catalyst provides an alternate, faster, lower energy reaction pathway, okay, where the energy of activation is going to be reduced. This is the pathway with the catalyst. This is the pathway without the catalyst. Okay. Energy diagrams. Now, I intentionally changed this just a little bit from what's in your book. In your book, these are about the same height, and I don't feel that they represent accurately or clearly what you need to see. So, because what this is comparing is it's comparing a kinetically controlled reaction with a thermodynamically controlled reaction. So in a kinetically controlled reaction, you have an energy barrier that is so high, the molecules are going over it, they come down to products, and the products don't have enough energy to get back over that energy barrier. They come down low, quite a bit lower in energy than the reactants. Sometimes this is called an energy well, because it's just like falling down a deep well. So they go over the barrier and down, and then they get trapped here. They cannot go back. This is a kinetically controlled reaction. It is not an equilibrium. Now, if you have an equilibrium, you have a totally different situation. The reactants go over a smaller energy barrier. We are not concerned with the height of the energy barrier. The reason we're not concerned with the height of the energy barrier is because it is low enough that the reactants can get over it easily, and it's also low enough that the products can get back over. So the reactants and products are both going over this energy barrier. This is a higher energy barrier, a lower energy barrier. And so this is an equilibrium. That is a kinetically controlled reaction. This is a thermodynamically controlled reaction. Kinetically controlled, thermodynamically controlled, also called an equilibrium. And so here what we're concerned about, since they are each going back and forth, and reactants are being converted to products, and products are being converted to reactants, the only thing that's governing this is the difference in energy between the reactants and the products. And you can see that here. So I think that by looking at these, I think that explains it pretty clearly, and hopefully you'll be able to remember it this way. Kinetics versus thermodynamics. Now, you can also have thermodynamics come into play in a kinetically controlled reaction. Just because thermodynamics are important in a reaction doesn't mean that it's necessarily an equilibrium. So here we're going to see an example of a kinetically controlled reaction. The energy of activation would be important here to both A and B reacting to give you C and D, as well as A and B reacting to give you E and F. Both of these are kinetically controlled reactions. And so here, the energy of activation for the blue reaction is going to be this energy barrier, and the energy of activation for the red reaction, or the reaction following the red line, is going to be this. It's going to be greater, okay? The red line reaction, A and B going to E and F, has a higher energy of activation than the reaction of A and B going to C and D. Now, this is normal. This is typical. This is the way that most kinetically controlled reactions, which give multiple products, are described. So what I'm talking about here is the higher energy transition state leads to the higher energy products. The lower energy transition state leads to the lower energy products. That correlation is typical, and it is what you will see the vast majority of times. Okay, now I'm going to show you a different situation, which is somewhat rare. Okay, so don't get confused and start thinking that this always happens. This is rare. And what it is, you have this energetic crossing. So you have the higher energy transition state leading to the lower energy products, and the lower energy transition state leading to the higher energy products. You do see that sometimes. So it's very rare, though. And so these reactions turn out to be somewhat important, because what you have is the reaction that is predominating. That's going to be the reaction that has the lower energy barrier. So this is the reaction that's going to be favored. And so what's happening is the unusual situation of the lower energy reaction giving the higher energy products. And sometimes it's difficult to synthesize higher energy products. Usually it's easier to get the lower energy products. It's easier to make those. And so these reactions where the reaction is favored to give a higher energy product or set of products, sometimes they can be very useful. So this is said to be kinetically favored because it has a lower energy of activation. The reaction described by the red line. The reaction described by the blue line is said to be thermodynamically favored because it has more stable products, lower energy products. Okay, but both of these reactions are kinetically controlled reactions. This is a situation in which thermodynamics, in other words, the thermodynamics comes into play. Okay, so the thermodynamically favored product is not formed, or is formed much less. Okay, these would be the products that you would see, and perhaps it would be the sole products, or it might be in just, you might have a mixture, and these might be obtained in much higher yields. Now, just some nomenclature here. These are transition states, energy maxima. Okay, these are energy minima, and these would be intermediates. The reactants and the products also, of course, are energy minima on the energy diagram. And so this is just to give you a little bit of nomenclature. Energy maxima, energy minima. Okay. Now, transition states versus intermediates. You just saw what the intermediates were. The transition state, a lot of reactions will have just one transition state and no energy minima. Now, notice what you have is reactants going through this transition state. This is your energy maximum, and this is going to be your energy of activation. And this is not a reversible reaction. This reaction occurs and goes to completion. But the point that I want to make is that you don't have these molecules come together and come to the top of this energy hill and sort of sit there and say, okay, what are we going to do next? And then look around, and then they decide that they're going to go on down. I think one time I read that the lifetime of a transition state, a typical transition state structure, is 10 to the minus 22 seconds. So this lifetime is so fleeting that the transition state is said not to really, exist for any time period. So this is just a structure, this is a geometry that these molecules go through, okay? It's just a transition state. So the molecules are said to go through the transition state. So notice, you might overlook it, but in your book it will say it's an energy state that the reaction passes through. It's just a geometry that this passes through. So they won't be observed. We get evidence for them by indirectly, and we are convinced that they exist, but they're never observed. And so don't start thinking that you can, that it has a lifetime that spends a few seconds there. It doesn't. It just drives straight through. An intermediate, however, it will exist. It can exist for seconds or even longer. They can exist long enough, in some cases, to be observed by different instruments. So this would be a high-energy intermediate, this particular one. This is a carbocation. Okay, so you have reactants coming together, going over an energy maximum, passing through a transition state structure. They are forming an intermediate. Okay, so here the CBr bond has broken. You have a carbocation. Now this intermediate and chloride will react and go on through the reaction and form the products. So this is a second transition state structure here. Notice it's also an energy maximum, but this is the important transition state. This is going to be the rate determining transition state. The rate determining transition state is always the highest energy maximum, okay? It doesn't necessarily have to come first in the transition state. Sometimes it comes later, but it is usually the first one. So this is a transition state. This is a transition state. This is going to be the rate determining transition state structure here. The Hammond postulate. So now, related to these diagrams, you can see here that this is going to be the transition state, the highest point on the diagram. So of energy versus reaction coordinate. And so this is just an arbitrary point that they selected to represent where the reaction has moved on down towards the product. And moving on down towards the product, the bromide is moving a little farther away and becoming more and more isolated. The carbon-chlorine bond has formed a little bit more. Notice up here in the transition state structure, the carbon-bromine and carbon-chlorine distance are about equal. Carbon is about equally bonded to bromine and to chlorine up here in the transition state structure. So this could be viewed as, say, half a bond, and that would be half a bond. So starting out, carbon is much closer to bromine. As the chloride comes in, bromide departs. And so up here, bromide is about half departed, and chloride is about half entered. So this is about the halfway point in the reaction. And so the point that is made from this slide is that you have to ignore this, ignore the arbitrary point that was selected, and focus only on the transition state structure, the reactants, and the products. Ignore this for a minute. And you can see that this transition state point is much closer to the reactants than it is to the products. The products are way down here, and the reactants are much closer. And so the Hammond postulate tells you that 2 points that are close on the reaction diagram are going to be more similar in structure. Okay, so it's telling that this transition state structure, the structure of this transition state is going to be closer to the reactants than to the products. So really, actually, it's telling you that this CBr bond distance should be a little less than that of the carbon Cl distance, okay? Because they're going to be more like reactants and less like products. So here, if it's an exothermic process, notice the products are going to be lower in energy than the reactants. So the products will be farther away from the transition state, and that tells you that the structure of the transition state will be closer to reactants because the points are closer together. On the other hand, if it's an endothermic process, the products will be higher in energy than the reactants. And so the points of the transition state structure and the products will be closer in energy. And so these will be more similar. The structures of these two will be more similar. Okay? And so the transition state resembles the reactants over here. The transition state resembles the products over here. I hope that's going to be clear. So that's the end of this sections 6, 4, 5, and 6. And now in the next few sections, we'll look more at reactions.